Hello everyone and welcome to Handmade here, our show where we code a complete game live on stream. We are in the middle of debugging our PNG reader, which actually hasn't been too bad so far, which I guess maybe that just means the worst is yet to come, who knows. So far it's been pretty smooth sailing in terms of interpreting the specification and so on. We did run into a little bit of a weirdness last time where there seemed to be some confusion. The spec seemed to pretty clearly state in two different places, two different rules for interpreting bit values for a certain part of the spec. And what we do know is that Sean Barrett was on the stream and he's already written a PNG reader, obviously for STB image. And he was pretty strongly suggesting that the part of the spec that said that the bits were reversed was wrong and that the bits were actually forward. Hopefully he is right. I mean, he should be right. He wrote the PNG reader, so he had to have gotten that right. But hopefully that's true, because if it's not true, then we have to actually reverse bits as they come in, which is a real pain in the butt, right? We'd like to be able to just read and use the value without manipulating the bits at all. So hopefully that is the case. I don't know if it is or not. We're going to find out, but we'll start looking at that today. And then we'll try to push forward. There isn't much more code to write. We've done most of the decoding work so far. There's just a transform thing that we have to write, which probably will be pretty simple. So most of the work left in finishing the PNG reader, which has been pretty straightforward, even though the spec is kind of old and weird. Most of the work that I think that we're going to have to do going forwards is just in debugging our interpretation and implementation of the deflate spec. So, and this is, again, since this is the deflate spec, it means that we could use this code presumably to do other things as well. If you wanted to read like a zip file or something that was compressed with the deflate spec, presumably this would read it. So it's actually kind of a generic piece of code in that sense, where this particular bitstream decode is presumably usable in a number of cases where the deflate compressor was used, or the encoder for the deflate decompressor was used, however you want to say that, where the deflate algorithm was used. So, what we think we know. So far, when we come down through here and we produce our decoding tables, so far it seems like this is pretty accurate. The reason why I say it seems like this is pretty accurate, when I say that I mean it seems like there aren't huge glaring errors in it. There might still be some subtle ones that only happen once in a while. But the reason that I say that it seems pretty accurate is because when we actually come through here, this assertion does not fire, which means that we actually do decompress the information in the tables and get exactly as much table data out as we expect. So if we were like totally decoding it wrong, we would expect that to fire. And now that we've gotten to the point where it doesn't fire, we can sort of assume that we're, close, right? On this part. We then do Huffman generation. This is basically, they have a certain way in which they've encoded the Huffman tables to try to make them concise. This right here decodes those Huffman tables from their sort of encoded version. It's not really that compressed per se. It's just sort of a concise encoding. That is compression, obviously. But anyway, this concise encoding of the Huffman then gets turned into something we can use to decode the Huffman more quickly by generating tables. Now, we don't know whether that is working properly, right? We implemented what we thought was a reasonable way to do it. We don't really know. So that's just purely speculative. Then we get down to this loop, and this loop, again, we have no verification of yet. So we don't really know if these are proper. We don't really know if this is proper here. We cannot, at the moment, I think, decode a full block correctly. So we know that we've got at least one probably glaring bug in there somewhere that we can fix to get us to a slightly smoother run. but at the moment we will be focusing on from here down because we do have some reason to believe that this part is working relatively correctly. Now, again, that's not necessarily the case in its entirety. There could be some subtle bugs in here that just allow you to produce the same number of lengths, but you've got one or two of them wrong, or all of them are wrong in some subtle way that doesn't affect how many of them you did, and things like this. So we don't know much about this part here in terms of the accuracy of the Huffman tables, but we do know something about the bit encoding, and we think we've got that part right. Everything else is still suspect. And then this part right here is the first time we really did this code last week, Sunday, I guess. I'm sorry, 2 weeks ago Sunday. We were off last weekend. So this part right here is probably got plenty of issues in it, and we'll sort of start to suss those out as we go. What I will point out is we're now at the part of the process where structured art can start to help us. I don't know if we're quite there yet, but we're close to there yet. What do I mean by that? So if we open up this file with GIMP that I made as our test, look at these lovely mushrooms. We can go in here and look at the first part of the file that we created, or at least I thought we created. Where is it? Sorry, that's not the top there. It was right there. And what you can see is I've been very careful to put in the first row of the image here, I've put a red dot and then 2 black dots and then an increasing alpha. Now in the last row of the image, I've done a similar thing. I've put 1 green dot and 2 black dots. So what we would expect to see when we start decompressing this is one of those two things. Now, I don't remember seeing in the actual spec yet, I'm sure it's in there somewhere, but we didn't go looking for it, whether these images are encoded with the bottom as the first line or the top as the first line. But regardless of which you can, that's why I put 1 on each, regardless of which one it chooses, we will expect to see that structured art appear. And that should start to give us a clue as to whether or not we are even decoding anything correctly. Now, the thing to remember here is we can modify this, and we can, in fact, start with much simpler things too. In fact, I might go ahead and do that here as well, create another one for us to use. I can do something like just make a single 8x8 block, for example, and I can make sure that we know all of the values in this 8x8 block. Let me make sure that it has an alpha channel. But what I can do here is I can make sure that we set these values to things that we know as well. And then it's a lot easier, again, for us to just kind of plunk through what we're looking at as we start. And again, this is just, the reasoning behind this is very simple. The idea is that if you know what you expect to get when you decode something, you can read in the debugger exactly what kind of data is coming out of the decompressor, and you can start to have an idea about whether or not it's even remotely working properly, right? And furthermore, if we create a highly structured piece of artwork, we can also potentially see where we're starting to go wrong. You know what I mean? So we can sort of start to see what happens when we get to the end of lines or things like that. And we can sort of start to see like where do we start to screw up if we get some correct values and then get some values that are incorrect. You know, why is that happening? So we should be able to create some things that help us and are sort of waypoints for us in that regard. And so here's an example of an image that sort of does that. And I'll just make one more here. Sort of the half-bright versions. So this, gives us a pretty clear, we can all understand what this should look like when we actually look at it in binary. We've got 8 pixels across. We have a known color on the first pixel of every row, and we've got a blue pixel at the end of the first and last rows, just so we can kind of see where that watermark is. And that, I think, is, again, totally reasonable. Let me just go ahead and maybe I'll do one more thing. Well, no, I won't. So let me go ahead and export this as a ping as well. And that way we can also load this in and have a smaller test thing to look at. Because the other one's pretty big. It's more of a complete test here. And so we can load that one in and just get a good, and we can also force it here. We know we want it to use the 32-bit format. That's what we're looking for here. And I guess, we've also got this compression level stuff, which we could play with. But again, that's just if we wanted to try like making the file simpler. If it's 0, maybe it doesn't use any compression. I don't know. In which case we could look at an uncompressed one. So we probably do want both of those. Like we could do something like this, right? Where we export one of them, and then I can also export another one of them that's specifically compression 0, where this gets cranked down to the bottom. I don't know that we care about any of that. We skip those blocks, so those should be fine. And yeah, there's really nothing else in here that we care about really. So if I just set that to 0, we can see if that creates a materially different file compression-wise. And if it does, we can see, like, again, get some more information about where we're starting to screw up. So that's really all I'm talking about there. Just, again, creating opportunities for us to find our bugs. It can be hard when you're dealing with really robust, intricate data. Because again, you just don't know what you're dealing with. So if you just have something very, very simple and basic, that can really help you zero in on those bugs quicker than spending all your time trying to sort through what you're looking at in the debug view. Okay, so if we go ahead and launch this here, let's actually go ahead and take a look at that. Well, I don't know if it's uncompressed. It's compression level 0. Maybe GIMP still does some light compression on it. I'm not sure. But I'm interested to see what happens just if the file like doesn't have the compression part in it. I'm just interested to see, right? Because it could have, remember there's this B-type 0 block. It's a block that just doesn't have any of the deflate encoding specified in it. It would be interesting to get something with a little bit of that in it because we would like to handle that as well. And we also thought that we had a to-do here. So this, we need to do this as well. Martin's correctly pointed out that that's not, and you know what, I should... So if we look here, first of all, this read the Huffman stuff here is actually done now. This is the place where we actually want this, I believe. Am I right about that? So I think... yeah, so I think what happens here is B-type 2 is the one that actually has the tables in it. B-type 1 is one where we actually have... seed the Huffman with the built-in Huffman tables. This is one that we are going to have to handle. So if we now take a look at what will happen on the compression 0 one, I'm just curious again before we get started. This is 8x8 compression 0, I believe is the name of the file. Am I right about that? Let's take a look. Yeah. So it's 427 bytes long. Let's go ahead and step into the PNG read here. So when we get in here, this is marked as supported, which is good. We come through here and we look at the pixel setup. It's not bfinal, which of course is a little weird because you'd think there'd only be one block to encode that, but maybe it's every row is different. I don't know. Anyway, let's take a look. Okay, so it did exactly what I hoped, which is that if we set the compression level to 0, we just get this kind of file, which is a file that has no deflate encoder in it, or at least it doesn't look like it does yet. So it will allow us to test this part as well. So if we consume a U16 here, in both cases we get a len and the nlen. The nlen is not a value we actually need. It's just an error checking value, it looks like. It's supposed to be the ones complement of len. And so we just have to see if that's right. So it says here that those don't match. Let me see what's going on there. I think I did that right. Maybe I did that wrong. So there's len, right? And we can look. And there's nlen. So that is definitely, what did I do? Because that looks exactly like it should look. My okay. So is this actually doing integral promotion on this? It looks like we're getting integral promotion here, assuming that this is doing the same thing that will do. So I guess that's forcing us up to above a U16, which we really don't want. Let me go ahead and force it not to do that. Or try to anyway. Just to really make sure. Not sure why it would do that, but yeah, there we go. So it was just an integral promotion. It wanted to expand. When you did this operator, it wanted to expand it out to 32 bits. Just using C's integral promotion rules, which I will never for the life of me understand why they are the way they are. I'm sure there's historical reasons for it. They're not reasons I would probably agree with, but whatever. No one cares what I think. So it's fine. We go in here. We need to endian swap this because I believe we read that the length value is actually wrong. It's encoded the opposite way around, I think. Now, I don't know if that's actually right because we said, is it supposed to be? So if we look here, we see 264. If we were doing an 8x8, right? And each one was supposed to have 4, that would be 256, which is how many pixel values we'd have to be included. Now, we would also expect 8 row transform values because they didn't know very much about image compression, which it's hard to blame them. It was a long time ago and people weren't that knowledgeable about that sort of thing. In general case, back then, they weren't experts. You don't generally want to do transforms per row. They didn't know that, so they put 1 transform per row. And so I suspect that that's just what we're seeing here, 8 times 8 times 4, plus 1 transfer value per each row would be 264. What that suggests to me is, regardless of how we interpreted the spec, it looks like that length value is not endian swapped, right? Because the endian swapped version of that's going to be huge. And I don't think there were 2,049 pieces of data in this file. So I suspect that that's an error and an underflow, right? So I think what we want to do there is we want to sort of fix this, right? And we can also check on this here. We might as well put I mean, we don't really care about making this robust, but we might as well. So I think we're just going to say that based on our experience here, is not supposed to be endian swapped. I had a to-do there, so that meant that I wasn't really sure what the spec was trying to say, so that seems fine. And so here we go, sort of reading that data out, and that looks like that read correctly. So, the nice part about that is it looks like we already have the ability to read, a simple PNG, so that's good. And if I look at there it is. So, this all came out correctly, and I think probably the data is correct here. I don't know. We should probably find a good way to look at the data. But in the meantime, in lieu of doing that at the moment, I think what I'll do is I'll just go ahead and look at what decompressed pixels ends up being. So if you take a look here, we've got decompressed pixels where it does this allocation here with the width, the height, the 4, and the extra bytes. So this is the decompressed, it's not really decompressed, but it's decompressed data goes in there. let me see here. Do we just copy that into dest? We do. So yeah, okay. So when we're done in this supported section here, I'll just go ahead and skip to the end. Why does it not break on that line? Yeah, all right, great. Visual Studio, as always, making debugging harder than it has to be. Visual Studio always excels at this. Here's decompressed pixels. Let's take a look at what is in it. So what I want to do is I want to get this to show basically the bitmap. I think I can force it to 9, potentially, hopefully. Yeah. So here is the row transform value. Here are the pixels that we're seeing in that. Sorry. And I want these to be 32-bit. So there we go. Right. Oh, you know what? No, I take it back. I can't do that because of that row one is the one, that one's off. So I'm going to have to actually do, it's 8 times 4, which is 32, plus the 1, so it's 33. So this is the actual sort of scan I'm going to want to use, I guess, right? So as we come through here, we're going to be writing these pixels. You can see us writing them in here, right? And so what I'm going to look for is I'm just going to look to make sure that this does come out to be what we think it should be. And this will also tell me something really important when I look at this, because it is, again, structured artwork. This will give me a clue as to what the actual encoding value is here. Does red come first? Does green come? Does red come first, or does blue come first, and so on? So taking a look here at these values, so wait a minute, did I do that math wrong or something? So there's supposed to be 8 pixels. Each one should have 4 bytes, so it should be 32. What am I missing here? So there's the row transform value. That should be 1 pixel, right? And, again, what I can do, I don't know why I closed it, probably because I wasn't thinking. But if I go ahead and open this, you can open in Visual Studio. Okay, that's interesting. Let's see here. Open with, that was probably talking about a different file. That's what was going on there. So let me go ahead and zoom in here. So if I look at this, I expect red, blacks, and a blue. All of the alpha values should be full, I would think. But then again, I don't really know how they're choosing to encode this. I guess I don't know what GIMP is thinking there. So let's do this, just 'cause I don't know. So if I make a new layer and I put it down here, so all of that stuff was supposed to be opaque. So I'm not sure what to make of that. Maybe that's not true until I just did the thing I did, where it's not the bottom layer, but we'll got to look at this a little bit more closely. Because you see what I'm seeing here? There's all these zeros in here. I don't really understand. I also don't understand what that is doing there. I guess that's because my assumption, and again, this is just purely speculative, is that when I paint into this pixel, GIMP is off a little bit on its radius and put a little tiny bit of red into the next pixel over, just a tiny little bit. That's my assumption. Anyway, moving forwards, as you look at this, you can sort of see my confusion. Looking over here, you see this FFF value that is blue, but it's still 0. So here's my guess. And I don't know what else to make of it. So this data does now line up if you assume that the alpha channel is just wrong, or arbitrary? I don't know, because if you look at what we're looking at here, this all like looks somewhat plausible, right? Although actually no, it doesn't, because that looks like a green there. Ah, so you know what? Here's the thing I will say. We don't know what these row transforms are. So now that I think about it, and they're actually set, like one set to one, one set to two, or two of them are set to two. So I guess here's the thing. We'll have to go look at what those row transforms are. That probably is what it is, right? Because those, even though we said compression 0, maybe what GIMP does is GIMP still applies row transforms. Even though compression level 0 turned off deflate, maybe it still applies row transforms. And that would explain why we're seeing sort of like values that line up a little bit but don't really make sense the way we would expect them to. That seems logical to me. Like, so for example, if this was a difference between the pixel above you and you, this would make a lot of sense, right? In fact, it looks like a difference between the pixel... Oops, oh, I had to do it too soon. It looks like 1 is difference between you and the pixel to your left, and 2 is you and the pixel to your top. That's what it looks like. So just purely based on what I saw there, that's what I would expect to see in the spec. This is good. I'm glad we're in this place, because today, let's forget about the Huffman for now. Let's get those transforms working, because we need to do that, and now we have what we think is good data coming out that's not compressed. That gives us an opportunity to get the transforms working without worrying whether the Huffman's working, which is a more complicated part. So I feel like that's really a good thing here, right? So let's go ahead in here and take this, this decompressed pixel stuff to the sort of make that happen out here. I'm going to go ahead and have a thing that's like final pixels, which is like the thing that we take the decompressed pixels and sort of wrap them into. So I'm going to do a set it to 0 here, and then I'm going to allocate pixels once we actually know that we're supported in here, and we are able to actually do a decompression on the data in the file. Then I'm going to decompress, I'm going to allocate final pixels worth of space that we will like sort of extract the decompressed pixels into, right? So once we get to the end here, we're just going to assume that we're okay. And we're going to go apply those transforms, those row transforms as written. Do I have this in the right place? Let's take a look here. Yeah. So coming down here, we're going to have to go row by row. Oh, no. What happened to 4Coder? I don't think we've ever had it crash on stream before. That's the first time. Let's take a look here. What's going on? Draw file loaded. Should have probably installed the source on this machine because we actually could look at it. So that's a drawing problem, which is kind of bizarre. I wonder if that's related to all those flashes we're getting. I should update the version of 4Coder on this machine. It's a little out of date. Let me go ahead and close this. No. That may already have been fixed, I don't know. But I don't think so, because I don't think there's been any rendering updates. At some point, we should try to debug that purple flash. because it's weird. And it happens a lot on this machine, and it doesn't happen on other machines that I've seen. Like I get that once in a blue moon on other machines, but this one happens all the time. Makes it seem like maybe it would be a good idea to debug it on this machine, since it seems like it's pretty, it's got a pretty high hit rate, whereas debugging something on a machine that doesn't have a high hit rate is very hard. All right, so let's try that one more time. Again, all I want to do here is just have a final pixels. This is just a thing where I can put the final data that will get passed back to whoever in the application is like asking for this thing, right? So when you said parse PNG, you know, you called me and you handed me this this PNG file, and I'm supposed to return you like some kind of a set of pixels. So that's going to be what that value is. So when we find that the thing is supported, right here, we're going to go ahead and allocate space for it, and then at the end we're going to go through each row that we ended up with, and we're going to try to put the transform data into the untransformed state. So we're like undoing the transform that the PNG compressor did when it compressed, before it compressed the row. In this case, it didn't compress the row, so there was no need for it, but Bink did it, sorry, not Bink, GIMP did it anyway. Sorry, apologies, Rad Game Tools. All right, so if I go through here and I just loop over my rows, I know that I have height, number of rows. And what I want to do is I want to go through each pixel here. You know, I could just make it easier on myself, just make this be Y and X. I mean, we know what those are, right? So for each of these, what we're going to do is at the beginning of the row, and I can sort of set up two things here, which is like, and I can pull this out in a separate function in a second because it's going to be pretty self-contained. So we know that our source is coming from the decompressed pixel buffer, which has that row thing in each part of it. And then our des is going to be the final pixels. So what we're going to do first is we're going to read the transform. And that's just a single thing that comes out of the source. And then what we're going to do is we're going to read the R, G, B, and A values out of the source. And then we're going to apply potentially some operation to them. And from there, you know, go from there, right? So what we need to do now is we need to, and like I said, looking at it, it looks like their left neighbor difference and top neighbor difference were the two that looked like they were in there. I don't actually know. That was just my guess. So we got to go look at the PNG specification and find out what the actual, what those actually are. So where was that stuff? Let's look at transforms. A number of transformations are applied to the reference image to create the PNG image to be coded. The transformations are applied in the following sequence, where square brackets mean the transformation is optional. Alpha separation, indexing or RGB merging, and then sample depth scaling. Okay. When every pixel is either fully transparent or fully opaque, the alpha separation, alpha compaction, and indexing transformations can cause the recovered reference image to have an alpha sample depth different from the original reference image, or to have no alpha channel. This has no effect on the capacity of any pixel. Transformers are considered equivalent, and the transformations are considered lossless. Encoders that nevertheless wish to preserve the alpha sample depth may elect not to perform transmutations that, okay, all right. If all alpha samples in a reference image have the maximum value, then the alpha channel may be omitted, resulting in an equivalent image that can be encoded more. Okay, so that actually was the case with our image. It just doesn't seem like they actually did that. Unless when they say omitted, they mean just wrote 0 or something. But no, they didn't. They actually encoded it, I think. I don't know. It looked like, because it was the right row length, I think, with alpha in it. So I don't think that actually removed the alpha. In either case, we probably don't care about that because we will never have an image that probably does that, but we can look. So one thing I don't like here is they're not telling us how to do it. So this is really the wrong section to look at probably, but hey, it's a good backgrounder. We need to look, because like it doesn't say how it encodes that fact, right? Maybe it encodes that fact by just saying that the file isn't 4 deep, it's 3 deep, right? Maybe that's what they mean. Indexing. If the number of distinct pixel values is 256 or less, and the RGB sample depths are not greater than 8, and the alpha channel is absent or exactly 8 bits deep, or every pixel is either fully transparent or fully... You know what? And here's probably why GIMP didn't do it. I manually selected RGB A8. So even if their compressor would normally look and see if it was going to emit the alpha table, I sort of forced them not to, right? So maybe we should allow them to do that just so we can make sure we handle that case. We may need to handle that case because for like a backdrop scene that doesn't have any alpha, maybe, I don't know. It's hard to say. We can cross that bridge when we come to it. It shouldn't be a very hard modification to make, to say the least. All right, so blah, 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 blah. No one cares. So let's see. Assuming we don't care about indexing, RGB merging. So it's basically saying can reduce to grayscale. This one, yeah. So these are things we probably just don't care about. These are all if you wanted to support the full spec and cared a lot about it. We don't. We only care about the things we're likely to see. So unless we see that, we're not going to do it. Okay, so this is just something that expands values that are at different sample depths. We don't care about that either. Each scan line is transformed into a filtered scan line using one of our defined filter types. Compression, chunking, reconstruction. Okay. Not sure I follow this here. 4th reduced image, 5th reduced image, 6th reduced image, 7th reduced image. I'm not sure I follow that. Pass extraction splits a PNG image into a sequence of reduced images where the first image defines a coarse view and subsequent images enhance this coarse view until the last image completes the PNG image. The set of reduced images is also called an interlaced PNG image. 2 interlace methods are defined. The first method is a null method. They're stored sequentially. So I think I don't care about that either. This makes no sense to me. What this here makes no sense at all. I mean, I can see... I guess this is just how they chose to encode smaller versions of it. So here's the 4 pixel version. It does this one, this one, this one, this one, right? And then, so rather than doing like a wavelet where you would blur out you'd take the average of like all of these or some other wavelet transform, and then you would do the difference from the average and encode that progressively. They just actually literally take specific pixels. Who knows why? Probably memory bandwidth concerns, or maybe probably because they didn't know about wavelets. I don't know. Both of those two things probably. Wavelets are bad on the cache. So let's see here. Okay. PNG standardizes one filter method and several filter types that may be used to prepare image data for compression. Transforms one byte sequence to scan line to an equal length sequence of bytes preceded by filter type byte. That's what we're looking at. Filter type byte defines specific meaning to apply the specific scan line. The encoder shall use only a single filter method of an interlaced PNG image. It may use different filter types for each scan line in a reduced image. So we're using the non-interlaced versions here. So we're talking about multiple filter methods. So exactly as we expect here. So what are those filter types? That's what we really want to know. That's not in here. So let's go ahead and look at the filter type section. Presumably that's defined somewhere. Filtering. Here we go. Okay, so filtering transforms the PNG image. Its goal of improving compression. Yep, that we know that. Only filter method 0 is defined by this international standard. Other filters are reserved for future use. So they're talking, I believe, though, about this. So I believe they're talking about this one. So filter method 0 is the part they're talking about, only has a 0 in it. That's just the overall filter bank type. Each individual row for filter method 0 has a different filter type for that method. So that's what they mean by only filter method 0. Here's the actual set of filters. So here you go. 0 just means, hey, use the original. 1 means, subtract from the, I assume these are, what's it, the byte to the left, the byte in the previous scan line, the byte corresponding to B in the pixel immediately before the pixel containing B. So does that mean the pixel 2 pixels back? Or I don't quite know what they mean by that, but I'm interpreting that to mean 2 pixels back. So X is the byte being filtered. A is the byte corresponding to X in the pixel immediately before the pixel containing X, right? So basically that's saying if we were talking about the red channel of the current pixel, we would talk about the red channel in the pixel 1 to the left, right? That's all. B is the byte corresponding to the previous scan line. So that's just, again, the same thing, but top. So this is exactly what I thought, right? In C is the byte corresponding to B in the pixel immediately before the pixel containing B. So that's 2 pixels back, I'm pretty sure. So my guess, I mean, I don't understand why you would have C in there. But my guess is it's because since this was like low res and had an indexed mode and stuff like that, dithering was probably a thing. So I'm guessing that maybe that is a, like alternating pixels is a common thing you would see in like bit twiddly like pixel art, right? And since this was made in that era potentially for that sort of thing, that makes a lot more sense than if you were making one today. That doesn't sound super plausible. Like, sure, that might be one thing if you had lots, but you would probably you'd probably want the pixel up and to the left before you would want the pixel 2 to the left most of the time, I would think. So if you were gonna pick one more thing to have, it wouldn't be 2 to the left. But you know, I'm just guessing that because of dithering, maybe that's where that comes from. I don't know. Hard to say. Anyway, those are pretty straightforward. Assuming that I'm interpreting C correctly as 2 to the left, those are pretty easy to understand. We wouldn't have much trouble implementing those, so that's fine. So here are the actual filter types encoded based on these prior values. So to reconstruct, Type 0, it's just the value. That means no filter is applied. Type 1, we add in the prior pixel value. Now, I don't know how we add it in. I assume that it's just an 8-bit wrap, not an 8-bit saturate. Here we go. Unsigned arithmetic modulo 256 is used so that both the inputs and outputs fit into bytes. So it's basically like saying if we were at 230 and we were supposed to add 100, we would wrap around rather than saturate to 255. We'd end up at a lower value, right? So we're doing a wrapped unsigned add, which, I mean, just a wrapped add, doesn't matter whether it's signed or unsigned. So we're doing a wrapped add there, and that's pretty straightforward. So I'm glad they specified that. Okay, so we add either the pixel to our left, the pixel to right above us, and I should say the channel right above us, because it's a specific part of a pixel. It's the red, green, blue, or alpha channel. Then we have this sort of average, which takes both the previous 2 pixels and splits the difference. Okay. And then we've got a path predictor or path predictor with A, B, and C passed into it. And that is this function right here. It says that the calculations shall be performed without overflow, which suggests that they should be, I guess, computed in 32-bit or 16-bit, so that if you add 255 to 255, you actually get a value greater than 255, not a wraparound value. Just assuming. So that seems reasonable. I don't think we really need anything more than that. So let's set ourselves up to apply this transform. So looking at what's going to happen here, we know that we need 2 prior pixels, and we also know that we need a prior scan line. Now, when we look at how this is accessing, despite what I might have assumed, they never use values to the left of the top pixels. Like, they never look a scan line back and then over. At least if they are, I'm not seeing it. It looks like they only look behind us on this row, and they only look above us directly. So the reason that I bring up this as being odd is I would have thought they would have. They don't seem to. I also think it's a little weird because they say, for filters that refer to the prior scan line, the entire prior scan line and bytes to the left of the first pixel in the prior scan line shall be treated as being zeros. But when would they ever look at a value that was to the left of the first pixel in the prior scan line? How would you get there? Can you see it? Because I don't see it. Bonus points to anyone who can see how that ever actually happens. For right now, I'm going to assume that doesn't actually ever happen, because if it did happen, that means that I'm misunderstanding this, because the understanding that I have about what they're asking me to look at can never look there. So if you actually can look there somehow, then I messed it up. Like, I'm not thinking about this properly, unfortunately. So that's just how that is. So what we want to do here is we want to do a prior row value, right? And looking at the prior row, it's telling us that it wants us to have it be all zeros. When we look back there, we're supposed to find just pure zeros, right? So what I will probably do is I will probably say that we want to have a 0 row here that we look at, and then every time through we just set the prior row equal to the row that we just did, right? You know, something like this. Actually, this sort of thing, right? So every time through, we'll remember where we started this row, and then at the end of that, we will swap that back in so that the next person looks at that row separately, right? So we would have liked to have done this. We would, I mean, this is the kind of thing we almost would like to do in SIMD, because we're going to do the exact same thing to every channel since the filter type is only allowed to be one filter type. We are going to apply the same thing to R, G, B, and A. So the right way to do this would be to load it into an M128 and just apply it there. I don't really want to do that here because it seems like maybe that's a little bit overkill for this reference code, but that's what you would do because you're doing literally exactly that. Furthermore, you're doing it for everyone, so you could actually do this. If you're trying to load PNGs quickly, you could apply this filter using SIMD really efficiently. So I'm just going to put a note here about that. So I would just point out the fact that if you did want to make this this part of the process run quickly, I think you certainly could. Now, what I would point out is that may be one of those cases of just being an optimization person for no reason, because I would assume, and I could be very wrong about this, but I would assume that the Huffman decode is going to be the disaster here because it's such a bit twiddly serialized process that really can't be accelerated very easily no matter what you do, at least not to the kinds of speeds you would want. So this is the part of the process that could be trivially sped up with SIMD, not to mention trivially multi-threaded because every row is only dependent on the prior row. So I feel like you could do some pretty easy stuff there where you just broke the image up into bands that could be done separately, I suppose. Although I guess the look back makes it a little bit harder to do it that way. So maybe it's not quite as easy because of the way the look back works to do the multi-thread, but I'm sure you could still figure out some way to do it. Anyway, point being, the SIMD part, though, it seems really easy to do because 4 wide would just be 4 channels at once, and I feel like that would be good. Maybe I'll just say that, not to overstate the case. But since RG, B, and A are all handled the same, this would be a pretty easy case to be for that. However, I don't think this is probably the slow part of the process. We'll find out, but I don't think it is. So in here, we need to know the row filter type. So we're going to have to switch on this transform. And because we get it every row, it changes, right? So we're going to have to handle each case separately here for the transforms. And if we look back, we're only expected to go up to 4. So in the event that we actually found a value that wasn't one of those values, that's an error. So I'm just going to print it out if that's the case. Now, I was calling these transforms, they're really filters according to the spec. I mean, I don't know what the difference is between those two. I wouldn't have called this a filter. This sounds like a transform to me, but all right. So assuming this is, this is called a filter, let's just name it that so you know in the spec what you're looking at. So we get an unrecognized row filter, we'll complain. Each one of these then is going to be its own loop where it does something different. So each of these is going to behave a little bit differently. In this case, this is just a straight copy. So this would be something where we just copy all of the pixels to the source. And we can do this 32-bit wide if we want to, because you know, we can do this. Right? Because we know that we're going to copy entire chunks of 4 every time, and we're only supporting the 4 wide values at the moment. Now, I don't know. We did bit depth 8, color type 6, which I think color type 6 is RGBA, right? Yeah. So we know that we're always that format, and the artist just has to re-export it if it's not in that format. So we're just going to say that that's the case for now. We may have to support color type 2, at which point we would have to make this be a little bit different, because it would have to support, like even filter mode 0 would have to support an extraction phase, right? It has to go from 3 components to 4, so it has to read 3, pad to 4, and write. So, you know, just pointing out that's a little bit different. This would be a +4, but this would be a +3, and the alpha channel would get ROPed in. It would get added in there. So we can support that eventually if we find that we want to, and we may have to, right? All right, so moving along, if we're in case, you know, so now we're looking at something similar to this, certainly in each case, but, you know, we've got sort of a different process to go here. So what I'm going to suggest is when we're actually going through these, I might suggest that we just do per channel, since each channel gets handled the same way. I'm thinking that maybe it's more like this sort of a thing. And so now what we want to do is start to, sorry, change that, is start to make this a little bit more, I think it was called little x was the value. I don't really want to do that. Let's call that v or something. So what we want to do here in case 1 is now start to follow that table. Here it is. So the reconstruction filter for case 1 is we just want to add whatever the previous byte was, the previous pixels was. So what we want to do here is say that I'm trying to think of exactly how to say this. So we want to be able to read from the previous pixel, or in the other case, the previous 2 pixels, right? So there's a couple different ways we can do that. One is we can just backfetch from them. The problem is if we want to write tightly into the result, then we have the problem of how to handle the gaps, basically, like the sort of the parts of the image that we haven't quite gotten. So I guess the question is, do we want to make it easier on ourselves to filter and just allocate more space and fill that space with known information? Or do we want to do something saucier than that? I don't know. I mean, I guess the other thing that we could do here is actually still do 32-bit and just reconstruct. And that would allow us to do something like, I guess it's A pixel and C pixel. So we could save those two pretty easily. So for example, when we come in here, you know, we would say A pixel and C pixel are both going to be equal to 0. Then when we come in here, you know, we sort of say that after we process 1 pixel, right? So if we were to actually do it this way, then what we could say is, oh, all right, so whatever we end up with at in the destination, the A pixel is going to be equal to that, and the C pixel is going to be whatever the A pixel was, right? So it's pretty easy for us to store those two and write tightly into the thing. So maybe we should do it that way. The reason I didn't really want to do it that way is because if you do it like this, then the problem that you end up with is you have to now process each channel separately, which is kind of annoying. You know, kind of an annoying process in and of itself. But let's suppose we want to do that. Then what I could do is just say, okay, you know, give us the value. So this is the sub function. So it's like trying to think of how to write this here. So if I said, well, you know what I can do? Let's just do this. So if I said, hey, PNG filter, here's the source pointer, here's the destination pointer that I want you to write to, I could just say, look, here's the pixel index, right? I'm the channel index, 0, 1, 2, and 3. And it'll just pick out which one it's going to do. So I can do that, and that would work. And since we know this takes the A pixel and the C pixel, we can just give them those two and write that function, right? That seems reasonable to me. It doesn't really need to read from the dest. Well, it sort of does because it's to and into the dest, maybe. Yeah. Let's do this. Right? So if we just wrote each of those in here, again, not sure how the compiler will, what the compiler will think about that. Hard to say. But again, each of these then becomes pretty easy for it to access. Because now it just does a bracket on each of them and it would just work. So that seems like it'd be pretty, I'm just going for easy to write here, not efficient. So we'll leave it at that. So then I think that allows us to just keep going. And I think that's about right for the loop. So then what we would need to do is we need the same thing here for each of these. Oops. I don't know what happened there. There we go. So for each of these, we need basically the same thing. Case 1 was the neighbor pixel. 2 is the upward pixel. So that one doesn't need to track these two. So all it's doing is it's just using basically a top pointer. And that's going to be the prev row or prior row. And so when those go through, that's going to do plus equals 4 here. So that prior row is the thing that's going to be placed in here. So you can see, okay, we've got filter 2, and that gets the input that it needs because it's only using A. I'm sorry, only using B as it goes there. So then we have the average. That takes both. So, okay, so that's the average of the top pixel and the left pixel, right? Oh, so okay, so I was reading this slightly wrong. Never mind. So this makes a little more sense that you use the pixel 2 to the left because it's doing a predictor based on the gradient of those two. That makes more sense. So never mind. I take it back. That's not just for dithering. That's a reasonable predictor. That's basically saying, hey, look, I'll look at the 2 previous pixels. Let me see what their difference is. We're going to use some predictor to figure out based on that what we think this one will be. And we also look at the top one, you know. So, okay, never mind. Never mind. I take it back. So that is a reasonable predictor. It's probably not great, but it's reasonable. So, okay, so case 1, case 2 are handled. Case 3 is not using C, so that's just this one here. C pixel goes away. A pixel remains. So in here we've got prior row. So that's good. And then finally we have the path predictor case. And that one actually needs everything. So that one needs prior row. And in both these cases, prior row has to be advanced as well. And we need to track A and B pixels. So yeah. Oops, that's not right. I guess I should just call that B pixel. There we go. So yeah, what we want to do here is just make sure that's all kosher. Can I get this out from behind my head? That would be helpful. So what we want to do in this case is we need to pass all of them to the, you know, this 4 one here. And then we have to actually write these. So I guess these are going to return a U8. That's the result of the filter. They're going to take an X, an A, a B, a C, and a channel. And yeah, some of them have some of these, some of them don't. So 1, 2, 3, 4. One off there. I believe what we said was that this one has only an A, this one has only a B, this one has an A and a B, and this one has all 3. Okay, so if we look at what's happening here, if we take case 1, it looks like we're just adding them together. Now I don't know. Again, I don't want it to do integral promotion here. I really want it to do 8-bit addition. Short of using SimDebug before, we can actually manhandle that a little bit more. I'm not sure how to convince it otherwise, so I'm hoping that will help. Here's the reconstruction for B. Same deal. Really, these two are the same, so we could just call it PNG filter 1 and call it in both cases, because it's just, you're just passing a different thing. We could just say right, because there's no difference between those two things. Yeah. Right, so you've got a pixel here. I don't know why I defined those up here. There's no point to that at all. So let's not do that. Okay, so we got 1. This will be calling 1 and 2 because they're both the same. This will be calling 1 and 2 as well. So we have a pixel in one case, b pixel in another, and we remember our destination version here as we go. That's all fine. This is the first one that actually is different, so these two have their own calls and their own, well, their own everything, really. Yeah. So current row equals dest and prior row equals current row, so that's all what we want. And that all looks pretty good. Okay, so getting back to here, PNG filter 3, that's pretty basic as well. It's just taking the average, right? So you want to add A and B together, divide by 2, and take the floor of that. Now, I'm assuming that that wants to be done non-wrapped. I don't know if that makes a difference. Well, it definitely makes a difference, right? So the reason that I'm a little concerned about this is because if the averaging function, if this line were to be taken literally, then A plus B divided by 2 would only actually produce the average of the bytes for values less than 128, right? Because for 2 values greater than 128, or where their sum is greater than 255, I should say, it will wrap, and then the divide will produce a much lower value than it should have. So it seems to me like you would want to do the result in... That just doesn't make sense. I can't imagine you actually wanted to do wrapped 256 there. Here we go. The sum arig A plus arig B shall be performed without overflow using at least 9-bit arithmetic. I'm like, that can't be true. I like how you literally said that and then immediately contradicted it. It's like, okay. Yeah. So what that means is this actually is x, well, so it's x plus the average, yeah. So this is actually x channel as a U8 plus the U8 version of the non-U8 right? Average of these two. So that we do want to be done at the higher bit precision. So we do the average at the higher bit precision. Then I want to divide by 2. So that will floor because integer division will floor automatically. So we don't have to do anything careful to make the floor happen, I don't believe. So then we can go from there. Let's just make sure this... Let me do this. I want to make this a little bit clearer. So there's our average that we've computed. And now I'm going to go ahead and cast that average to a U8 for adding, and then off we go. Okay. So now we get down to this path predictor, path predictor, I don't know what you want to call that. We sort of have a lengthy set of stuff that it wants us to do here. So we need to be able to take the absolute value of these differences here. So yeah, I don't know how we want to do that cleanly in this case. I might just actually use an if just to make sure we're doing it 100% correctly here. But anyway, here's what we want to actually have from the spec. Why am I not able to... Oops. I guess that's not something I can paste. All right, so P equals A plus B minus C. So... All right, the algorithm using this international is the adaptation technique to Allen path. The path predictor function code below. The logical function location ABC X predicts X. Okay. So again, taking them at their word, we need this to be wrapped. Oh nope, without a. So they're like, hey, unsigned arithmetic modular 26 is used. Parentheses only here and here. So half of the things don't obey that, but off we go. So I guess I guess it's this part right here. So this subtraction, or rather this addition, is the only part. They should have just been this plus, right, is the part. All the rest of this stuff is always not that. So happy birthday. Anyway, okay. So what we want to do here is we want to actually do at the end one of these again. So we want like our path result here to be something. And then we're going to do that add again in a wrapped arithmetic fashion. But up until that point, we're going to be in La La Land, so we're going to go ahead and use U32s for that. So the first thing we're going to do is compute this p-value here that they're asking for. And that's basically like the basis color or the basis channel level that we're going to then difference to see what all the differences are between the various pixels and that basis value. All right, so we've got PA, PB, and PC. So here what our problem is, I mean, what we could do is do this signed, right? And we could say, okay, we're going to do this up conversion here. Put it into S32s. Let's subtract each of these. And what I can do is just say if PA is less than 0, PA equals negative PA. So for now, we'll just do it manually. We could try to think of doing something clever later on, but I'm not going to bother right now. So what we're going to do there is just we'll do the subtraction. We'll test to make sure we're not negative. If we are negative, we'll fix it, right? So now we know that each of those is absolute values. So then we get down to here. So we have a PR looks like the that looks like the payeth value. So that's what we want to actually compute. So basically what we're saying here is, okay, if PA is less than or equal to PB, and PA is less than or equal to PC, then we set our payeth value here to A. Whatever A was coming in. So I suppose I should actually get those values too. All right. So I read out each of those values. I produce my little dance here. I check all of the differences off the basis to get those done. Then we go ahead and do this like this little dance here. So it's PB less than or equal to PC. There we go. So we grab all those values out. Then when we're done with them, we're basically going to pick one of these things to use, either the top value, the left value, or the value 2 to our left. We're going to pick one of those to start with. We're going to return that, and then we're going to encode the difference off of that, is basically what it's doing, right? So yeah, that's really all that is. PB less than or equal to PC, yeah. Otherwise, we just use C. Okay? And, you know, if we want to encode this exactly like it was written, it'd be this. So I think that's all of the filters in this case. We have not actually created that 0 row thing. Yes, we are hiding a previous value. I don't know that I care about that. But here, let's do this. So here's our reconstruction function for the PNG filters. I'll just copy this whole thing out. And put it up there. That way we don't have any variable shadowing and stuff for common names like dest or whatever else. We can remove that outer layer of bracketing as well. So, and then this thing can just send us the various things we need. So we need to know what the decompressed pixel thing is. We need to know what the final pixel part is. And then we just need the 0 row. We can talk about that in a second. That's sort of a separate issue. And there's a couple things we could do there. There's a couple of different ways we could create that. And in fact, you know, I probably will do it that way. So I'm going to say that we just do those two. We'll talk about that in a second. But what I'm going to do now is when we come down here after we're done with everything, where we were doing that before, so in here when we reach the final block, and you know, after everything's been decompressed, then what I'm going to do is I'm just going to call that filter reconstruction function and have it reconstruct. So let's see what else we need. Okay, right, we need the width and the height. That's a pointer. So is that. All right. So now the question is, well, what are we going to do about this? Here's what I'm suggesting. And I realize this is a little janky, but again, just for ease of implementation at first. So let's just make 0 row point at a single 0. And then what we could do is have there be prior row advance set to 0. So everywhere that we were doing b pixel here, we'll just make that be prior row advance. All right. So what we'll do is once we actually get a valid row to start reading, we'll set it to 4. Up until then, we'll just leave it at 0. So it'll just keep reading out of the same 0 right here. And that'll be that. Seems pretty straightforward, right? So I think that's a reasonable sketch of something that handles all of the transforms. Don't quote me on that, but I think it's roughly right. So, you know, when we get down here, we should be able to now take a look at what that's doing. So let's just see if we're even in the ballpark. I'm going to go ahead and take a look at the final pixels. See what that value actually is. Can I get a watch window here? Let's do this. Let's get memory down here. There we go. So what I want to do is I want to grab, okay, this is all I don't care about. So I'm going to grab final pixels and put it down here. This is what we're actually writing into. We now are 32 columns. That's our entire image. So I just want to see what we end up with here, right? And so that transform's working pretty good so far. This is now exactly what I expect to see, which is good. So there you go. That's exactly the row that we thought we should get. Let's see what happens now. Okay, now we're into case 2. Again, that is what I expected to see. So that's totally right. What we can see here as well is if we assume that we're looking at this, it looks like it's top down, right? This was the first thing we saw. So it's not bottom up, it's top down for the PNG. Red is encoded as the top or bottom. It looks like it's encoded this way. So it looks like it's R comes first, then G, B, and A. R, G, B, A. Looks like what they've encoded, right? So wait, no, I lied. It's alpha channel first, right? No, this is, no, I'm wrong. This is byte-wise. My brain wants to always look at these things reversed because I'm so used to looking at them. But so this is byte-wise. RGBA, RGBA. Yes, RGBA, RGBA, RGBA. So it starts with R, ends with A. That's all we needed to know. And off we go. So do we ever hit this path predictor case or this averaging case? I don't know. Let's find out. No. So we don't know. Those could be totally wrong right now. It looks like our basic predictors were fine. Because we look at this image, this looks right. So yeah, I think we've got all of those working okay, but these, you know, these could just be wrong. So we should try and get those tested somehow as well. But at least we got the basics in here. So let's see. So maybe what I'll do is I'll force a crash the first time it goes in there. That way, like when we find one, we'll know, and we can just verify that it's working at all. Because they might just be buggy. We don't know. Okay. So hey, guess what? We correctly decoded a PNG image. That's the good news. The bad news is it's only the very simple kind, so we still have a lot of work to do because now we've got to go get the Huffman stuff working. But at least now we know the filter part, and we've got code for the filter part. That code looks like it'll be pretty easy to debug, I suspect. Now, I say I suspect because, well, there was a bunch of stuff about do you want wrapping or not, and maybe we got something wrong where we didn't quite do the wrapping correctly, so it's still not 100% sure that we are doing it correctly. There could be bugs in there. We don't really know. Let's go ahead and now try the compressed version of this image. I'll leave that up actually in case we need to refer to it. And try to get that working. And that'll be probably, we won't have that working by the end of the stream. Because if we had that working, we would be basically done. And I suspect it's going to be at least one more episode before that. Okay. So let's start down that path. And let's see where we're getting. I don't really remember exactly where we're at here. In terms of what we have for the Huffman stuff. So I don't remember really how close we were to decoding anything. Let's see if we get, yeah, so we managed to get this decoded properly as I suspected. That part there, we don't really know if it's generating. This part here, we have no idea what we're doing either. But let's start to look at destination pixels and see what we actually are putting out. Oops. Meant decompressed pixels. Can you just type? Does that work? No, it doesn't. So it won't remember what we put in there, unfortunately. It always converts it to an address first. Visual Studio being super helpful as always by not doing what I want. Okay, wait, now I got it. Oh, there we go. Okay, so I gotta click that button, I guess. I don't know. Anyway, so let's see what we've got here. There's an 01. That is what we expected to see. We're still outputting stuff here. So this is the simple case, and the simple case, unsurprisingly, appears to be working here. So that encoded a big old run of zeros, which is also probably correct. How many of these we got? Let's just slide this over so we can see where the end is. That looks frighteningly correct. So we did Huffman decode one row properly, I think. That looks like the right answer. I'm not sure about that. No, that's correct. So if you think about what's going to happen there, it's using the leftward predictor. It's going to load this into the color channel. It's going to add 1 to the red channel, which is going to cause it to overflow from 255 to 0, which is the correct red channel. And then it's just going to be repped the entire way. Alpha channel FF, 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 FF. So this is the right row. We got the right row. So now it looks wrong. Oh, no, it doesn't. No, it doesn't. No, it doesn't. We may be okay here. We're all right. I'm like, it's one off, but no, we had changed this to 32 before because we were looking at just the decompressed image. Okay. So now let's see how we do here. What's our len value here? 24. That seems reasonable too. Off we go. That all looks good. Yep, that's right. So, I'll be honest, this looks really good. Yeah, I mean, so far we seem to be in pretty good shape for these rows here. So, that seems to have decoded the image properly, to be honest. Let's take a look at what happens when we reconstruct it, just to see, what we end up with here. So if we feed that image into here, can we get another memory window? You can have exactly 4 memory windows, ladies and gentlemen, because everyone knows there's not more than 4 places in memory that anyone might want to see. All right, so let's go ahead and get final pixels in here. Okay, got to put that little thing in there. Final pixels. Okay, so let's see what Final Pixels has to say about this. This one should be 32 wide. I mean, that looks right. That looks like the image. So, okay, so now we have decompressed both. We have decompressed a Huffman stream and a non-Huffman stream ping both correctly. So that suggests to me that our error, because if I remember correctly, decompressing the other image, though, it failed. That suggests to me that we have a subtle bug, not a, not like a really egregious bug, but like one that, only happens when the numbers are right, or in this case, or whatever, right? So that's good. That's reassuring. Where's the thing here? Okay. So there's a couple different things that could be happening here. First of all, one thing I would note is that this is a PNG that has an IDAT chunk that contains the entire thing. And so one thing that is different about the other image that we were having trouble with is it has multiple IDAT chunks. So one thing we could look for is, do we have a problem striding IDAT chunks? So did the thing, when we underflow an IDAT chunk, did I screw that up? Is that possibly where the bug's coming from? So one thing I do want to do is, now that we got this image under control, I want to just like scribble some stuff in here and make a more complicated image. And save that off as sort of another test. Okay. So I'm going to save this out. And you'll notice I kept these pretty hard, these first ones, just because I wanted some way of still correlating some semblance of like what the start should look like. So I'm going to go ahead and export that. I'm going to compress it at 0. And then I'm going to do the same thing we did before. Compress it as normal at 9. And then I'm going to try loading those. Just to see what happens. And if we get a little bit more of those like weird results there. Okay, so I mean, one good thing that one positive aspect there, right, is we've got the other filter types here. So that PayF filter is getting used. So we can start to debug that one now. The other thing I would say is I don't know why this thing, so this didn't actually do what we asked it to do, which was to always do final pixels. So it looks like it starts off with some rows that aren't that way. Oh God, okay. Yeah, it starts off with some rows that aren't that way, and then it hits right here. There's the 4, right? So we've got one forward in the middle of a lot of other stuff. No, I just... Sorry, I accidentally hit the mouse wheel. All right, so I think that should be good. So let's go ahead and get this started then. So that seemed to decompress properly as well. I'm not sure what's up with that, but I don't know how accurately it was actually decompressing, but didn't error. All right, so now let's take that assertion out and actually step through that and see whether we're getting what we think we're getting here. Okay, so jumping in, here's our A pixel and C pixel. They get initialized to 0. Our B pixel is the prior row. The prior row right now is also 0. So we go through doing our 0, 1, 2, 3 for A, B, and C pixels. We then remember what the A pixel was for next time's C pixel. We remember what the dest we outputted was for next time's A pixel. We should advance by, oh, well, no, it won't be 0 because this actually is the prior row here. So the prior row just happened to be 0 there. I guess that's actually true if this was the prior row. It actually had a red channel 0, so that's okay. All right, and we advance both of those and we come back through. So that does look correct. Whether this is correct, I don't know. We read A, B, and C here. So that's reading full red. Oh, sorry, no, that's just each of these. Okay, never mind. So that's channel 0. That's reading the red channel of A, B, and C. So it's getting, the pixel to our left was full red. The pixel above us was not full red. But that's not true. Was it? How do I get birds here? Is that true? Oh, okay. So that is true. Because we're on pixel 1, right? So that is true. The picture before us was full red. Fair enough. So we do P is 225, A is 225, P is, so is that right? A, B, C, yeah, it is. So that's all correct. So I mean, that looks reasonable. So what was the X of that channel? was 1. So this produces 0. It does. Okay. I mean, that looks reasonable to me. We should go check what the actual image values are, just to see. But like, we're producing the correct value for the alpha channel, which seems pretty unlikely if we were super wrong. So we're probably only subtle. If we're wrong on the path filter, we're not like way off. We're only a little off. All right, so let's finish that up. Yeah. Yep. Yep. So I mean, you know, that looks pretty good. Let's try. This part still work too. Yeah, by no means. Don't remember that setting. Okay, so let's see. We got all of that. So yeah, this is looking pretty good. So I guess we're kind of now down to a question of like what's going wrong with the more complex ones. And I don't know. So let's go ahead and start. I guess we got to start looking at the more complex case, and we're gonna have to. We could try to make we could try to break that case down into which parts are causing us the problem too. Like we could try to isolate parts of that image and actually go like, okay, here's the thing that appears to be causing us the problem, you know? So that, you know, we can kind of see how that goes. But like we crash somewhere, right? Yeah. So we like overwrite where we're supposed to be, or something happens. Let me see where we're at. I just remember this is where we were at last time. So yeah, I don't know if the source is bad. The dest is definitely bad. So we definitely just advanced too far with the length value. So we know that something's busted here. What I would like to know is, I'm curious about that IDAT chunk situation. I want to know whether or not the IDAT chunk state is part of the problem here. So I'm going to go ahead and say let's set a break on when we underflow to see whether that is screwing it up. It's unlikely. I think we probably just have a bug in our Huffman decoder, but I just want to check the obvious stuff before we go diving into that, because might as well check the obvious before the harder stuff. So here when we do a consume size, we look to see whether we have any more stuff to output. First of all, we didn't hit the underflow, did we? No. All right, so first things first, my hunch is at least correct to 1 degree, which is that this is the bug that we know about, like the telltale, the crash, right? The obvious symptom that there's a problem. That is coming after the IDAT chunk changes over. So it's not obviously the case that my sort of thing I wanted to check is safe. It could be that we actually have that problem. So let's take a look at what that implies. So this, oops. Here's the file thing we're reading from. We have drained out our contents entirely here. So we have another one that's 8192 chunk, and it's got a pointer here to the contents, and then that's got a next pointer too. One thing I don't know, so is file first I mean, I'm assuming that this hasn't already been consumed, but I don't really know if that's true. I guess what I'm asking is, are we accidentally reading the same chunk twice? So how does that work right now? All right, so every time... Oh, so maybe this is the first one, though. Yeah. So maybe we haven't changed IDAT chunks yet. Maybe I'm just wrong. Okay, yeah. I'm just being stupid. This is just the first one. So it pulls the first one. And this, now we expect this one, 2074, that one should move up to be first, right? So that one goes ahead, it gets the content size out, it should get this contents pointer out, and it does. And now it should move this up to be this one, 540, right? Yeah, and it does. Okay, so never mind everything I just said, it was incorrect. Let's run again and see what happens. Okay, so no. We have proven that it's not that. We do not change IDAT chunks before we hit the bug. So my previous suggestion that it was unlikely that that was the problem proved to be true. And we know there's a bug somewhere in the Huffman decoding that you just don't have happen when you don't have a big enough image, right? Or certain sensitive values or whatever, right? Now this makes sense because, like, if you think about how this thing was set up, if you remember all the stuff that we've been through so far to talk about like things like the extra bits and all that stuff, if you have a very small image, then the LZ runs that you're encoding, where you're doing, you know, the backwards lookup stuff and all that, those pieces are not going to be very large, right? When your entire image is only 260 bytes long, its entire encoding decompressed, there's not going to be a lot of times for you to do runs of 10,000 things, right? So all of those fiddly little, is the table set up correctly to decode the number of extra bits and this, that, and that, right? All of those things are not really in play as much with a small image, so lots of little bugs that we may have had when dealing with some of the tweakier parts of decoding those run lengths and things like that, those just wouldn't have come into play. So it makes a lot of sense that we're seeing a bug on a big image that we don't see on a small image, and so, you know, this is hardly surprising. That said, unfortunately, it's hard to know where to look. One thing I will say is it does look like we don't need to reverse those extra bits, so that was good because that was going to be really annoying. Anyway, so looking at where we're at here, one thing that might be good. So we don't know if maybe we've got an error in our tables here. We could probably spot check our tables just one more time to make sure that there aren't errors in the tables. Could be some errors in these tables. So that's something we should probably look at. I'll definitely take a look. The other thing that I want to see is it would be nice to do a coverage check. So when we have the simple images, if we know that we're decoding a simple image correctly, but we're not encoding a complicated image correctly, what I might ask is, are there entire code paths that aren't being hit on the simple image that are being hit on the complex image? So before I end, I'll end for the day on that note. Before I end though, I'm just gonna go ahead and put an assert 0 in like every path. And we know we're hitting this one and we know we're hitting this one. We watch them both happen. But what I've done is I've put ones in each of these. So now I can just run it on the one that works and just see. Like, I know that works. And I can actually do it on this one, which is probably the... well, actually, this one has more runs in it, so let's use this one. Or it should have more runs in it anyway. Okay, so we know we hit encoded len less than or equal to 15. We hit encoded len equals 18. Now remember, this doesn't mean these code paths are right. It just means that they have been run. We've hit 17. We've hit... Okay, so one interesting thing here is, right, this code never got used in the ones that actually work. So this one has not been used. It's worth noting, right? And you'll note it's a relatively complex case, right? It's a rep val, like looking at a previous one. So like, you know, probably want to look at that more closely and just see what's going on. You know, are we actually reading the right number of bits or doing the rep count there? You know, who knows? We probably are at least reading the rep count right. The rep val, maybe not, though, right? But probably because, yeah, I mean, we're looking backwards one on it, so yeah. Anyway. But, sorry, where were we? We were on this case. So the len tab bits used here, this case where we read the extra bits and add in, that case was getting used. So this one right here. This case was getting used as well. All right. So if we look there at just purely like whether or not a case was used at all, we still don't have any idea whether our averaging case works. But that's neither here nor there because nobody apparently uses that one yet. This case, encoded len equals 16, we did not call on the good version of this thing. Now, let's take just a real quick look. I'm going to go ahead and put complex in here and see if that one calls it. So it doesn't. I'm going to go ahead and see if this one calls it. It does. So, you know, still not really that indicative that there's probably a problem in it, but it's worth noting, it's just worth noting, that we do have one code path that is only called on the case that fails and not called on the case that works. Probably not really all that much to read into it, but it's just worth noting. So let's take a closer look at encoded len equals 16, just to see whether there's something there that's, you know, kind of obviously busted. So where is that again? That's not in here. Here it is. Copy the previous code length 3 to 6 times. The next 2 bits indicate the repeat length 0 equals 3. 3 equals 6. So we're going to consume 2 bits. Our rep count is 3 plus that. So that does seem right. Code's 8, 16 plus 2 bits, 1, 1 plus 2 bits. I don't know what that's trying to say. I don't understand the example. Oh, I see what it's saying. So it's saying if the first code was 8, which is actually a code length of 8, then the next code was 16 plus the bit 1 1, the bit pattern 1 1. Then another 16 of bits 1 0. That will expand to 12 code lengths of 8. So the first 16 is saying repeat 8 3 plus 3 times, or 6 times. And the next one is saying repeat it 3 plus 2, which is 5. So it's 1 for the first one, which already would have been handled in the previous case, 6 reps, and then 5 reps. I mean, it looks like that's what we're doing. So I don't think we've done anything wrong here. So even though that case, and I mean, I can certainly take a closer look at it. And just make sure that it's functioning properly, but it seems likely that it is. So we're on value 282. So we're down here at this. So what we're going to do here is we're going to say we want to repeat 3 sevens, right? 1, 2, 3. Seems reasonable. So that seems like, I don't think that's wrong. That seems right. So I would say we just still have a bug in the decompressor here somewhere. I'm not going to look for it any further today. I think we have a complete PNG decompressor right now for the cases we care about, except for this. So we have one more thing to implement, which is to put in the built-in Huffman tables. Hopefully that's not too hard to find from the spec. But the only thing I think we need to do is figure out what we're doing wrong in here, like where we've got something a little bit wrong. Because we are decompressing now Huffman and non-Huffman pings, as long as they're simple. So we've just got something wrong when we try to go to something more complicated. I'm going to go ahead and go to the Q&A. But that's pretty good. We're pretty far along here. Hopefully this means it won't take us too much longer before we're done. Ratchet Freak said the len and len is so the decompressor can resync with the compressor. If a block got corrupted, the compressor emitted an empty block by looking for the byte 0000FFFF, mostly handy for byte streams. But how often does the compressor output that block? And why wouldn't you just have a magic value or something that you block or something? I mean, does that really make sense? Or why not just make the IDAT blocks restart themselves? Just seems like a bad way to do it. Rooktag says C is up and left. Is that true? Did I read it wrong? The byte corresponding to B... Oh, you're right. Okay, well that is really nice if that's the case, because if that's the case, then it explains this part, right? Which was the part that was really kind of annoying to me because, yeah, I could not figure out why they were saying that. Okay, so it is what when I was like, oh, that's weird that they would do the 2 over. They weren't. And I was like, they should have done up and to the left. It looks like they did do up and to the left. Let's see here. So that means cpixel doesn't really ever have to be there per se. Well, I mean, I guess we can do it. It's just the previous, cpixel is just the previous bpixel. So instead of cpixel equals a pixel, it's really just this, right? So the up and to the left pixel is just whatever pixel we read as b this time around before we advance b. Keegan Gale, did I see 4 semicolon in your code? What's that for and how does it work? So you probably did see it in the code. I don't necessarily know where it is. Okay, yeah, here it is. So for reasons that I couldn't really tell you, I'm guessing that they are because the compiler was crappy. Visual Studio used to give you an error on that. They used to say that you had a while loop that always evaluated to 1, like a conditional that always evaluated to 1, and it would give you a warning, which of course if you have warnings treated as errors means it won't compile your code. The fix for that was just to use a for loop with nothing in it, because if you put nothing in a for loop, then it just is an infinite loop. And so this is the way that I now habitually do it instead of doing while 1 to avoid those previous warnings. I don't know if they still happen, but they were quite some time, like Visual Studio 2005 through 2013 or 12 at least, I think. So anyway, if you want to have a loop where you just want it to loop forever until you issue the break statement, that's just how that works. In the memory window, when you were writing the decoded pixel, you were writing to some memory that you have not allocated according to the ASCII representation. There were some strings about a path in Windows. I don't think you're right about that. I mean, what you have to remember is when you allocate memory, you get memory that's been used for something else, potentially, right? When you allocate memory with virtual alloc, the page that comes back will be filled with zeros. I think by requirement, I think virtual alloc has to fill a page with zeros before it gives it to you. I think that's required. But everyone upstream of the actual virtual alloc call can just recycle memory. So when you call malloc, you're not going to get a cleared page. You're going to get a page that somebody used and freed before you. Does that make sense? So I don't think we were writing to memory that we didn't allocate. In day 55, when you create the hash table, you added your to-do on getting a better hash. That was a joke, right? Because I didn't think we'd ever really need a better hash. I was just saying that everyone always puts in use a better hash function and then it ships like that, right? So that was kind of a joke. But what you would see if the hash is not good enough is that you end up linearly probing most of the time, which just degenerates to a linear search. Like, you can answer this question yourself, sort of. So a hash table, which we usually use hash tables with exterior chaining, right? So what we do is we have hash tables, and the entries in the hash table point to effectively a linked list of everything that hashed to that value. So let's suppose that your hash was awful and always returned the value 5 or something like that, right? Well, if it always returned the value 5, then everything that you put in will go into hash bucket 5. That means that everything that went into the hash table would just create one giant linked list. And every query into the hash table, therefore, is just a linear search of a linear linked list, which obviously defeats the purpose of having a hash table. So the thing that is a problem if you have a bad hash function, if you start feeding a lot of things to the hash function that all hash to the same location, you end up not getting the speed of a hash table, you get the speed of a linear search. So the worse the hash, the closer it is to linear search, right? The better the hash, the closer it is to O1, instantaneous, right? There's a Visual Studio plugin that lets you see images in memory. It's called Image Watch. It was pretty useful when I did the PNG decoding. Yeah, so that I agree that'd probably be useful. I don't super love plugins to Visual Studio. We've had a lot of issues with like trying to do stuff with just the one Nsight one or whatever, and it just, I don't really want to go down that road. That should be built into Visual Studio. It's kind of, it's lame that it's not, but. John DeResta, okay, it looks strange. Usually it's sold with OXDD or OXCD, if I remember correctly, or maybe just stack memory. So when you allocate memory, it absolutely will never be filled with OXDD or OXCD or anything like that, unless you are using a debug allocator that explicitly does that fill. So basically, allocating memory is supposed to be as fast as possible, so a memory allocator will never fill it with values. If you get back memory that's filled with values, that value should be 0 if it came from virtual alloc, or it should be garbage, but never a constant value. If it gets filled with a constant value, that means it's a debug allocator, and you'd better have known you were using a debug allocator, because if you weren't expecting to use a debug allocator, something's up, right? The same should be true for stack memory, because again, stack memory should be filled with zeros or garbage, but not a constant value, unless debugging is on. Now, I don't know if they've changed something recently where like stack memory gets like flooded with something to avoid like stack attacks, like stack overflow attacks or something like this. But you know, I hope they didn't do that. So I guess what I'd say. All right, I don't think I see any other on-topic questions here. Try a big image which compresses very well. Yeah, well, the image that is what that is. We did provide a big image which compresses very well. Probably what we'd be more likely to decompress okay, even including whatever bug we have, is a big image that doesn't compress very well, because that would be filled with lots of tiny runs and literals, and that would probably work fine, right? So yeah, you know, I suspect that, you know, if I had to guess, if we look at what's happening in the test image, there's just a giant run of white here, and a giant runs of all zeros here. And my suspicion is that we're not interpreting some of those larger run Huffmans correctly or something like this. You know, if that makes sense. So if we actually had an image that was filled with data, like a photographic image where it was very mixed in terms of the pixel values or runs or anything, I suspect that one might actually work. Right, like, because again, that's not stressing the LZ. It's like a fairly uncompressed image, and so I think we'd have more luck with that. Quick shift on Linux. Would you use calloc instead of virtualoc, or is there an alternative? Yeah, I think you'd use memmap. So mmap is probably what the low-level allocator is. Yeah, so this is probably what you'd be calling instead of virtualoc virtual free, it'd be memmap mem unmap. Not C Alex. C Alex or whatever is gonna go if that's gonna go through some intermediate nonsense. Sergeant Rumby, will you integrate the decoder directly into the game or into the simple processor? Directly into the game. It won't be used at runtime. Well, it won't be used in the shipping version, but in development, it will be used inside the game to hot load quick exports from Photoshop. That's why we're doing it. All right. Oops. Close everything down here. All right, thank you everyone for joining me for an episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along with the series at home, you can always pre-order the game on handmadehero.org, and it comes with the source code, so you can play around with it. If you want to try your hand at debugging the PNG stuff, now would be a good time to do it. It's mostly working, but we know we have a few problems in there. It's a pretty tough little debugging problem, right? It involves like a fairly complex input-output stream and a spec to look at to see what you're supposed to be doing and so on. So I would say if you want a little bit of a challenge, spend a few hours tonight seeing if you can find the bug or any, there's probably more than one bug. See if you can find them before tomorrow's stream, before we start looking for them together. It's be a pretty good exercise. All right. That's it for today. I'll be back here tomorrow to finish up that debugging process. Hopefully, we'll be finished by tomorrow because we actually have all the filters in place too. So maybe if we're lucky, we'll either be finished or mostly finished by the end of tomorrow. Who knows? It's hard to say with debugging. You never know how long it's going to take to find a bug. 2 hours may not be enough. We'll see. Until then, have fun programming, everyone, and I'll see you on the internet. Take it easy.